screen. Hopefully you're seeing that.
Yeah.
This X mean, I mean, you circled it, but that's the,
Yeah, it's wrong.
okay. For X greater than or equal to 0, the horizontal line y equals 2 is an asymptote for the graph of the function f of x. Which of the statements must be true? So this is like, this graph here is good. I kind of need to redraw something here. So let me just redraw it here. We only care about the positive side. We actually don't know what's going on over here. And it's always better to draw the asymptotes as dashed lines.
Okay.
And here's what it tells us. It tells us like option 1 is we don't really know what it's doing, but it eventually does that, or it does this. We don't know which way, but we know eventually it approaches that. Is that okay?
Yeah.
Okay. So I'm going to circle the correct answer. And can you visually see why that would be true?
Limit as x approaches infinity. So I'm confused because can't it not equal 2 since there's an asymptote there? That's why I was.
So the limit is what it approaches, and that's the same thing. So
I see. So it's just saying on both sides, or as it approaches infinity, it'll approach 2. Okay, yeah.
So here's the, I don't know, the summary. When you have a horizontal asymptote, y equals a number, whatever that number is, this means the limit as x approaches infinity, f of x equals that number. So what I wrote down here at the bottom is like meant to be, if it says it has a horizontal asymptote, then this thing must also be true on the right. If it says this on the right, then it must have a horizontal asymptote.
So then is there something like that for vertical asymptote as well?
Yeah, I could make one up here if you would like.
Well, it would just be like the same thing if it's like.
Well, so let me just draw a graph here, just try to. So let's just say it had a vertical asymptote at x equals 2. And it can mean a lot of things, but let's say the graph does this like that. I could ask you, what is the limit as x approaches 2 from the right? So 2 from the right means from this direction. And what y value does it approach?
Okay.
Positive infinity.
I see.
It could also be the case, though, that from this side it approaches maybe negative, goes down this way. I don't know, but like this is key up here that I'm boxing in, that horizontal asymptotes correspond with infinities. And then I suppose in the same way, vertical asymptotes sort of, I mean, this is sort of true. Because it could be like plus or minus infinity. These are one-sided limits. So there's a few variations on this. So I don't know. Is that clear?
Yeah, that makes sense.
Okay. All right. So I'm looking at 4 as being the next one that needs corrections. Is that right?
Yeah.
Okay. All right, given this piecewise function up here at the top, x plus 2, if x is less than or equal to 3, for x minus 7, if x is greater than 3, which of the following statements are true about f? Okay. There was a jump. All right. So, okay, so to do letter I, let's talk about that. To do letter I, we have to first find the limit as x approaches 3 from the left. And then we need to find the limit as x approaches 3 from the right. And to do that, it's essentially, because 3 is the breakpoint or the dividing line.
You just plug it in for x.
Yeah, so it's 3 plus 2, which is 5. And then it's 4 times 3 minus 7, which is also 5. Okay, so that's true. Yep, confirm that. Okay, it's continuous if the following is true. So let's go through that because this is just definition stuff. The limit from the left equals the limit from the right, which equals the f of 3 value. So we already know the limit from the left is 5 and from the right is 5. And then you just have to evaluate the function at that point. Well, you've already done that. It's this left side. So that's true.
Huh.
You didn't mark that as correct. So do you recall what you may have thought that would have led you down the path to say, no, it's not true?
For 2.
Say that one more time. Yeah, for 2.
For
Yes.
2.
Yes.
I honestly don't remember. I just knew that like 1 was correct, so I just went with that. And yeah, I don't think I even like.
That's okay.
I
That's
don't know.
okay. Because you said something here about x equals 3. So it's basically like the first graph goes up and then it hits a point, and then the other graph also goes up, but they're
Right.
they both hit there, so it's okay.
Yeah. That's why I didn't mark anything on B and C. I mean B and D, because I was like, maybe, I don't know.
Yeah.
Okay, that makes sense though.
Right. So let's just say it was 4x minus 6 instead of 7. Number 1 would be false because it would be 3 plus 2 and it'd be 4 times 3 minus 6, which would be 6, and so these would be different.
Okay.
And then
So in that case, the limit wouldn't exist.
It would not exist.
It would not be continuous because they're different.
They wouldn't be continuous, and there would be a jump discontinuity.
Okay.
So it might be that they're all 3 true, although it's not an option.
Gotcha.
Okay. 5, 6, good. 7, good. 8 is discontinuous.
Oh, I just forgot to the other discontinuity.
Yeah, the question's actually not written quite right. It should say find all x values for which the function is discontinuous, because it's somewhat yeah, okay. So yeah, yeah, you had it there. You just needed the words vertical asymptote next to x equals minus 3.
So on that one, it's just like anywhere that I factored it. So then anywhere where the bottom equals 0, right, is a discontinuity. So
it is, but you have to do it in the order that you did, which is if the factors cancel, like you show here at the top of 8. I know you can't see and I'm looking at your test.
Yeah. I mean,
the top of 8 where it says x minus 3, when the factors cancel, that's a whole, just like you said, you do wholes before vertical asymptotes, then you look at what's left over. And if because there's not necessarily always something left over, but in this case there was. So at x equals minus 3, there's a vertical asymptote.
Okay.
Part C is good. Okay. We should do 9b.
Yeah, I just totally forgot how to do that.
Okay. It's really close. So you have the difference. You have the definition of a derivative right here. And it's x plus h minus f of x all over h. So that's the first thing is your formula has a minus h instead of plus h. This you can forget after this exam, but you have to know it for this exam.
Yeah.
So this, like, you got to get, this is critical. So in your problem, f of x equals 3x squared. And then f of x plus h means to put x plus h squared in for x. So 3. And then we talked about if you could do this really fast, that's best. So then you distribute. So you get 3x squared plus 6xh plus 3h squared.
Okay.
Okay, so now we have, so I'm gonna let me actually use a different color here. You need 1. Actually, let me not do it that way. You need 1, 2 things, and you have 1, 2 things. So then you put those, you feed those in, that's there, and that's
Oh,
there.
okay.
Okay. So and that's why we do this. And maybe that's not made clear in class, but you're just finding those 2 things. And then lots of sort of, I think it's kind of amazing how this works. So you do that minus, let me move this down. I'm getting it's a little too close there. Minus 3x squared all over h.
Okay.
And this is that line where we said, if you do it right, you'll have only terms with h.
Right, because the 3x squared cancel.
Yes, so they cancel. Boom, boom, they're gone. And then, like I said, everything's going to have an h in it. So that means that you're going to be able to divide everything by h. And that's the fundamental issue here, is that you can't put 0 in for h because you get division by 0.
Well, you have to cancel your h's.
Yeah, and so if you want to show full work, I don't know what your instructor's like, but this is 6x plus 3h. Then you put 0 in for h. So it'd be 6x plus 3 times 0 becomes 6x. But we're not done. That leads up to it.
Right.
So this word in the problem here, actually I didn't snip it in. The word in the problem here, let me snip that part in. This is really important.
Instantaneous.
Yes. When it says instantaneous rate of change, it means instantaneous. This means derivative. Okay. It means f prime of x. These all mean the same thing. And this f prime of x is the limit as h goes to 0, f of x plus h minus f of x all over h. So when you see the instantaneous rate of change, you have to know that you're going to be doing this f of x plus h minus f of x stuff. Okay. So your derivative, your f prime of x, and this is key. This is the whole key to like the first semester of calculus, is understanding that the instantaneous rate of change is the derivative. The derivative is 6x. But there's more, because you have to evaluate the derivative. You have to evaluate f prime of x at x equals 2. So you have to put 2 into this function.
So 12.
Yes.
Wow. Okay.
So B is really asking you to find the derivative through this difference quotient limit thing, get that function, and then put the value of 2 in.
So then 12. So 12 is your answer.
12 is your final answer. Like
okay.
That's what they're looking for. Okay.
Okay.
But there's so much that goes into that. But like in a previous class, like they'd give you a function and you just put the number in. Here you have to figure out the function. That's what the instantaneous rate of change is. And then you put the number into it.
I see. Okay.
Okay, part 2. Is that okay?
Yeah.
Calculator allowed. Okay. First thing I noticed about question 10 is the calculator is of no use in this. Which
I think I totally just guessed on that one. If I'm being honest, I don't remember why I chose that answer.
Yeah. So like do you see now that this is difference of squares?
Oh yeah.
And the bottom is actually also difference of squares, although it's a higher order. But
one. You do like GCF on the bottom and then difference of squares.
Yeah, so let me start out at the top. The top is x minus a, x plus a.
Yeah.
The bottom is x squared minus a squared times x squared plus a squared. If that's not clear, we should go through that, but
No, that makes sense.
yeah. And now then maybe you're like, oh, I shouldn't have factored the top, because what was the top?
X
X
squared.
squared minus a squared.
So then they cancel.
So what's left on the top?
1.
1. So this is the limit as x approaches a, 1 over. And this is the issue here is that if you were to put a in this bottom part, you get a to the fourth minus a to the fourth from the beginning, and that's no good because you get 0 on the bottom, 0 on the top too. But now when you put a in, and remember, you're always substituting for x, you get 1 over a squared plus a squareds, and that just means you have 2 a squareds.
Oh, I see. Okay.
Also, guessing, you want to develop a better strategy than going with a. That's no good. There, it's almost never a,
Yeah.
because a is there to intentionally distract you in these sorts of things. All right.
That makes sense.
So like here, can I give you one like this?
Yeah.
Real quick. It'll be limit as x approaches a squared minus x squared. I'm sorry. Now, you know what? It'll be exactly the same. So no, we don't want to do that. I was going to do a cubes, but I don't think that that's right either.
Okay.
Okay. You got 11 right, but my question to you is, how did you do it? Did you use your calculator? Did you guess? What did you?
On it, I probably just guessed again.
Okay.
The ones where I didn't show work, I'm guessing that I didn't know what I was doing.
I mean, you did well here to guess. So I kind of think you had to graph this. I don't know if you had time though to do.
Maybe I did use my graphing I used my graphing feature. I remember I used it for something. Maybe it was that one.
Okay. Yeah, the other thing you can do is you can just plug in values really close to 0, like 0.0001 in like the table feature of your calculator. If you remember how to do that, or just in the just the regular window, you can just evaluate the function at values really close to that.
Wait, how do you do that?
Let me see if I can pull up calculator here. I have one. Just give me a moment to get to where I can show that. Delivery, no, learning, students, tools, 283. There it is. Okay. Let me new share. Where did it go? There it is. Okay. So I got this virtual TI-83 up. Hopefully you see that.
Oh yeah, cool.
Okay. So one option is to enter the function here. And let me go back and get it. Where did it go? It was sine. Stop. Sine. I don't want second. Sine 3x. Right, over e to the x. Is that right? Second,
Yeah.
e to the x. Oh, was it -1? Yeah, it was
Minus
-1. Yeah, close parentheses. And then if you go to second table set and you set it to ask instead of auto, you'll see why that's really helpful in a moment. So you set that, and then you go second table, and then I said like 0.0001. And it's 8.2 e to the -4. Oh, it's the limit as x approaches 3 or 0.
No, 0.
So
can I see what the graph looks like?
Yeah, I was gonna. Yeah, let's do that. So we'll go to graph. Stop graph. There we go. Okay. Graph, and there you go. So this is where I'm kind of like, how did you get this answer? Now let me make sure I graph the right thing, because it doesn't look right to me. There it is. See, like to me, it goes through 0, and that's why I'm like shocked that you got it. You got marked for it. Sine 3x over e to the x minus 1. To me, it should have been 0.
Well, I thought so originally, like I can see like my eraser is like, I thought that e to the x minus 1 was gonna be like a really small number, like 0. And then I thought it was gonna be like division by 0. And then I was like,
it does go through 3. That's really interesting. There must be something wrong with the table then that oh, you know what? My mode, I have the wrong mode.
oh,
That's gonna cause me problems here. So it needs to be in, no, it's
degree.
in radian. That's really weird. Y equals sine 3x over e. Oh, I've got imbalance in parentheses. That's why. I'm so sorry. This is really poor on my part. Okay, that
Oh, I
will
see.
make it better. There you go. See how it's really close to 3, and then you can go minus 0.0001 if you want, and it'll be really close to 3. So you're like, oh, it's near 3, and that's one way to do these. And then if we look at the graph,
So how do you know to plug in like a really small number?
because it's really close to 0. It's saying as the limit as x approaches 0. So you choose something.
So if it was limit as x approaches infinity, you would plug in like a really big number?
You could. Your calculator will tend to give you problems if it's like not like if it depends if it goes out to infinity or approaches a value.
Okay.
So like that the technique I showed you doesn't work well at infinity, but it works really well at specific values. Yeah.
Okay.
Okay. Let me go back to our workspace and continue looking at this. So 13. We can cover that next, I guess.
What about 12?
12. Okay. Yeah, we can talk about 12. You got it right. So that's why I was like, oh, we don't have to cover it. Okay. You have to kind of get a feel for what things do. So one thing you can do here, let me give you some options. One option is you can graph this. Okay. Another is to use the table feature. A third is to kind of rewrite. When I say that, I think that's probably your best option here is at negative infinity, this becomes the limit as x approaches negative infinity to x squared e to the x. But this e to the x, let's just say it's e to a negative number. Okay, e to a negative number means it's 1 over e to that number. So at negative infinity, this thing looks like more like the following: limit as x approaches infinity, 2x squared over e to the x.
Mm-hmm.
So the question here is which grows faster? So if you're to graph these, you would say, oh, well, like, doesn't x squared go pretty fast? It does, but e to the x actually grows like faster, way faster. So this one gets to infinity first. And so because it's like 0 over infinity, it becomes 0.
Oh, okay. I see.
But I don't know that I like that. I guess I like the table or the graph feature also.
So when you rewrite it, you have to switch the like you switch negative infinity to you switch the signs.
Because yeah, kind of, but that only works because it's x squared here, and the positive and negatives cancel. Like if it were negatives, negative squared is positive. If it's positive, positive squared is positive.
Okay.
Hopefully that's clear. Um, But you got it right. I mean, probably would try some numbers out. Yeah, and so you don't have to go out to infinity. You can try like 10, 100, 1,000. Like that'll give you a pretty good idea of what's going on. But the problem is sometimes you do these large numbers and it can't compute.
Okay. $13, did I have the right reasons for picking that?
The numerator is less than the denominator, so that goes to 0. So I think you just, my guess is you just didn't remember the rule.
Oh,
But yeah, C is right.
wait, but he said A was right.
Sorry. It's as X approaches 3. Oh, okay. So this one would have been a good one to graph or use the calculator. So your reasoning is out of scope. The reasoning only works when it goes to infinity. I didn't see the limiting value. So again, like one option is to pick numbers like 3.0001 or 2.9999 and see like, does it approach the same value?
Okay.
If this was asking the limit as X approaches positive or negative infinity, the fact that the numerator is less than the denominator would tell you that this goes to Y equals 0. But it's not asking that, it's asking at 3.
So what you do is you plug in like a number
Yeah, and really close to it.
and then what would you get if you plugged in those numbers?
So you can do this in your calculator, but like let's put in 3.0001 squared. So this is 2 times 3.0001 plus 3 over, when you subtract 1, it's 0.0001 squared. So when you squared something down here, it becomes really small, right? It's like 0.00060 zeros and then a 1.
Mhm.
So it's really small. And this is some number on top. So what's a
30.
number? So that goes to infinity.
Right. Okay.
But you got to check the other side too, because it may only work from one side or the other. Well, because 2.99 is on the bottom here and you're squaring it, it becomes positive. But it's still a really small number. Small, not small, small. So it's like any number over a really small number goes to infinity. You know, a number, no matter how large it is, over infinity always goes to 0. So there's a few of these that you have to be aware of. So it's like number over infinity always goes to 0. Number over really small goes to infinity.
Okay. I see.
These are some things to remember. Okay, should we go through 14?
Yeah, I have no idea what I was doing here.
Okay, find the value of A such that the function is continuous. Okay. So they tell you, I'm going to snip this in. They tell you the breakpoint. The breakpoint is at 0, or the division line. So that means you need to, whenever you get a problem like this, you have to evaluate both sides at the breakpoint. And the breakpoint is 0, so you're putting 0 in there and 0 in there. Okay, and then 0 in there.
Mhm.
So the problem is maybe what's not clear is actually this is pretty good, because this thing doesn't work at 0, but we know what the limit approach is. It's the like the sine x over x goes to 1 because there's a 1 right there. Like that's a definition.
So if there wasn't, if there wasn't, like, if it was sine,
Like 6x.
it would approach 6. I mean,
Yeah,
it would equal 6.
yes. Okay,
Oh.
but there's this 3 out here, so that affects it too, but that's a side point.
So then if there was a 3, would it be like 18?
Yes, it'd be 3 times. So in this case, it's 3 times 1. So this left side becomes 3, or right side. I guess this is the right side. The left side is you're putting 0 in for x, so it's -2 times 0 plus a, so 3 equals a.
Oh, okay. So you don't need to do, so you,
This is not the most common way this question is asked. Usually you have to put the x value into both, and then you solve for a. It's usually like a linear equation. Let me see if I can make one up from a previous problem that you had.
okay.
Because I do think this will help here. Yeah, so let's do it this way. So let's say f of x equals x plus a, and then plus 7. And then this other one is 4x minus 7a plus 3. This is for x less than or equal to 3, and this is for x greater than 3. So this is the more common scenario that you're going to get. And it would be the same questions. It would say, let me snip that in. It would say, find the value of a such that the function is continuous. Let me snip that in.
You would just plug in 3 into
Yep.
each
into each. So it'd be like 3 plus a plus 7 equals
10 plus a.
4 times 3 minus 7a plus 3. Yeah, so 10 plus a. 12 minus 7a plus 3, or 15. And then you just literally solve for a.
Okay, so subtract 10 and then add the 7. So 8a equals 5.
Yeah, so a equals 5/8.
Okay.
That's the more common question. Yours relies on the squeeze theorem, which you don't really care about, but you had to know that by definition in your problem, you had to know that sine nx over x always goes to n, like whatever the number is right there.
Right. Okay.
You had to know that, and if you didn't know that, you're just stuck. It does look like, though, I mean, I'm sure you hate this, that you did circle the right answer and then you uncircled it.
Yeah, I know.
Oh, oh, frustrating.
Yep. That's why I don't like multiple choice. It's either like you get it right or you get it wrong.
Yeah,
Like,
I mean, one technique is to cover it up, so that you just solve it without.
right. Yeah.
All right, 15. Should we go on to 15? I'm gonna take that as a yes. Maybe you
Yes.
said that.
Yeah. Sorry.
Okay.
Maybe
Maybe
too far from the thing, I think.
Yeah. All right. Okay. Find the equation of the tangent line. So encoded in this right here is the following. Get the derivative, or take the derivative.
Yeah, I had the equation wrong, so that kind of messed me
Yeah,
up.
and so we're gonna know really well after tonight's lesson. F of x plus h minus f of x all over h. Okay, so your f of x is given. So we don't need to redo that, but we do need to figure out, well, what is f of x plus h? So f of x plus h is x plus h squared plus 3 times x plus h. And you have to be able to expand this quickly. And you do want to like distribute and multiply and do all that stuff like ahead of time. Like you want to get it down to this line for sure.
Mhm.
And so like I mentioned, you need two things. You need f of x, which was given, and then you need f of x plus h, which you now have. Okay, and you kind of did that here. Like you said, you had the wrong one. Your instructor marked you up for the slope, because of course you're going to find the wrong slope when you don't
Right.
have the, but you know, you had the right path here. You just needed these steps. So the limit as h goes to 0, and then you've got x squared plus 2xh plus h squared plus 3x plus 3h minus, this is very important, it's in parentheses now, x squared plus 3x, because there's two terms all over h. And then you distribute this negative in. A lot of writing. It's unfortunately, that's just the way it is with these. And then some things start canceling.
So your x squareds cancel, your 3x's, and then your h's because of the
Yeah, all
denominator.
over h. So yeah, so those that cancels, that cancels, that cancels, that cancels. And then the h terms go away too, because, or you cancel out h. So it's 2x plus h plus 3. And then you can finally put 0 on, so it's 2x plus 0 plus 3. And so your derivative, which is not what it's asking for, but your derivative function is 2x plus 3.
Mhm.
Okay, so now it wants the equation of the tangent line. So once you get the derivative, the second step is to determine the slope. And the slope is the derivative at a point. So your x value, it's because of that. That's why it's at x equals 1. So we have to evaluate your derivative function down here, 2x plus 3. We need f prime of 1. So 2 times 1 plus 3, which is 5. So that's
Okay.
your slope. And then you knew this from
Oh, and then
studying.
you use your, and then you just use the point that there, so your to y minus 4 equals 5x minus 1.
Exactly. You're done.
Okay.
And you're done. Yeah.
And then so then I had the right like idea. So you would just do like the like a pair, what's it called, perpendicular slope,
Opposite
right?
perpendicular. Yeah. So
Yeah.
y minus 4 equals negative 1/5 x minus 1.
Okay. That's the normal.
Yeah.
I see. Okay.
All right. So 16. I mean, we can get up to talk about that.
Yeah, we can go.
Okay. So you got A right. No big deal there. B should be -2, not +2. Do you see that it's the coefficients 2, and the coefficient of in front of e to the x in the bottom is -1,
Uh-huh.
and it's the ratio of those because they're the same.
Oh, okay.
All right, and then you got C. Great.
Oh my God, I totally just guessed on how to do 17. Like I had no idea, and I did it right apparently.
95.
I just chose 2 points on the thing and on the table.
This is really specific to your instructor, and it does work. There are other ways to do it, like to use let me give you let me snip this in and give you some options. But if this is what your instructor accepted, I mean, I'm glad you got it right. So
I was
here's
just so shocked that.
here's 3. So one school of thought, if you remember, it's x plus h.
Yeah.
One school of thought is to use these 2 points. That's x plus h.
Okay.
Because H is the next point up, or gives you the next point up. Another school of thought is to use these 2 points. That would be like
Wouldn't that
X
be-
minus H.
Yeah, that would be X minus H.
And then there's another, and these are methods you learn in numerical analysis classes. Another school of thought is to use the average of these, of the red and the black. But if your instructor accepted first and last, great.
Okay. So the right way to do it is to use 3 and then
3 and 4 would be kind of the, like if I didn't know anything about this question, if you said, hey, this is one I think is gonna be the test, I would tell you use 3 and 4.
okay.
And that may be why you got credit, because the instructor was so unclear with what you're supposed to do, and the first and last is a reasonable estimate. It's just not the best one.
Okay. That makes sense. So we did all of them in part 2. Can we go over 3 on part 1? Because I was kind of unclear about that one.
Absolutely, yeah. Let me get there. Was there? Sorry, I closed it out. All right.
Sorry, there's a lot of background noise right now.
No, don't really hear much.
Okay, good.
For which of the following does the limit not exist? Okay, let me snip it in. And you're getting, so here's another thing here. You're getting the style of your instructor's questions. Unless this is just an oddity, they like multiple choice. They like kind of these like 1 and 2, 1s, 2s, kind of things like that.
Yeah.
So, okay. So which of the following does the limit not exist? So the limit exists when the limit from the left equals the limit from the right. So basically, does it approach the same value?
Okay.
So let's just look at them one by one here. So here's 4 here. So does it approach the same value from the left and from the right?
Yeah.
Yes. 4 here again, it approaches from the left and from the right. Yes. Okay.
Mhm.
Here from the left and from the right, this is a big no, because they're different. Go ahead.
It has the same X value, but it doesn't have the same Y value. Is that why?
So these are the Y. You're looking for the Y value, like the limit.
Right. For the different Y values, so it doesn't work.
Yes, exactly. Okay. So it doesn't. The thing that's maybe troubling here, and I'm just gonna say it that way, is it like in this first case, it's defined up above, and in the second, it's not defined at all. The limit only needs to approach the same value. It doesn't have to actually exist there.
Okay.
Which is hard to like. It's uncomfortable. You're like, but it doesn't exist. Like, how can it approach the same thing? It does. I mean, it just, without getting into a lot of like unnecessary conversation. Like,
So sorry. On the first graph, the limit, it exists, right? Because there's a closed circle up above.
no, it has nothing to do with that. That's the idea behind graphs 1 and 2 is like, graph 2 is the better one to start with. They approach the same value, but it doesn't exist. Like that, like there's no value there.
Well, yeah, right. So then for 1, they approach the same value, but it does exist, right? Because
they both exist here. Let me draw. I use this analogy a lot, and I find this incredibly helpful. So there's a river. This is scenario 2. There's a river, okay, and you approach it from here, and I approach it from here, but there's no bridge. There's no bridge, okay.
right.
Okay, but we approach. We can see each other. We're, hey, how's it going? You're like, oh yeah, I could see you too, but we can't cross. Okay, but that's what that scenario is. The second one is, or the first one is, we do the same thing. We both approach, we can see each other, but the bridge is over here. There's our bridge.
Oh,
And you know, that's where the analogy doesn't really work, because we could just walk over there, but assume that we couldn't for the moment. And then the third one is you approach there, I approach there, and you have a bridge, but I don't.
I see. Okay.
And so it exists if we can see each other. We can see each other. Here we can't see each other.
I see. Okay. It's a good analogy.
It seems to work pretty well, but not perfect. All right. You've got to be able to do a difference quotient. I would either suggest doing 9b or 15 again on your own,
Okay.
so that you can do it and feel comfortable that you can do it. Like in 15, the only thing that might change, it might be x squared plus 2x. If you do 9b, it might be instead of
In 15,
3x.
you were saying it might be what?
Let me write those down. We'll just write them down here. So 9b, instead of f of x being 3x squared, it could be instead like 2x squared.
Oh, I see. Okay.
And 15, I think, was like x squared plus 3x. So it might be like x squared plus 2x. I mean, it's not going to change that much.
Yeah, so just changing the numbers.
Yeah. Or just work through it again as is, but you've got to get that difference quotient like down to the point where you wake up, you roll out of bed, and you know what this is. But I assure you can forget this. Like, this isn't one of those things that's going to come back and haunt you. Like later on, it's kind of like proofs in geometry. Like once you do them, you're over with.
Yeah, you never have to do it again.
That's what's happening here. But you got to be able to do this for this chapter, and then you learn a shortcut if you haven't already in in your studies, in your class. I don't know where you guys are at.
All right. All the rest, I think.
When are you doing your retake?
I'm gonna do it on Wednesday. Yeah.
Okay, so I saw you scheduled for, I think, Tuesday. So are you planning on us doing more review like this, or new stuff?
I wasn't really sure what I was gonna do. Probably
Okay.
more review. I was gonna do my test corrections before then and then give them to him.
Okay.
Yeah.
All right. Well, if you got test A, maybe you're going to get test B. So if you have any idea of what's on that, that might be helpful. So overall, there's a lot here to be positive about. You're real close. This is kind of normal calculus stuff that students don't understand the first time they see it. So
yeah, maybe on Wednesday we can just run through like some questions that are similar.
Sure, absolutely.
Like I don't know.
Absolutely. Is there anything else I can answer for tonight, or can we end here?
No, I think I'm good.
All right. Well, thanks so much for scheduling. I'll send you the notes and the screen recording out shortly.
Thank you. Bye.
Thank you. Bye now.